Hi guys, and welcome to Ecology Notes, Populations. In this lecture, we are going to be addressing what the carrying capacity of an ecosystem is and what exactly are the limiting factors that contribute to that. All right, so first we need to define what a population is. So population is a group of individuals of the same species living in the same place at the same time. So those of us who live in Salem, Virginia, we are a population of humans because we are all the same species living in the same place at the same time. Here is a population of sea otters. They're adorable. Population of Hamadryas baboons, only adorable when they want to be. And a population of hornbills. They like to put holes in your shoes. Population growth is dependent on factors that probably are going to be pretty familiar with. So birth rate, death rate, immigration, and emigration. So usually people know immigration is bringing things in, emigration is when you leave. So populations can grow when you're adding more organisms than are taken away. So if we look at human population growth, we can see that humans' population was quite low, and then all of a sudden our birth rate was high, but our death rate was high as well. But with the advent of better medical care and sanitation, more babies started surviving, and we had the same birth rate with a lower death rate, and that's when our population really started to rise. Populations can also shrink. That's when more organisms are taken away than added. So say people have less babies, but the death rate increases for some reason. So if we look at the Malayan tiger, they're an example of a population that is shrinking. In Malayan tigers, their birth rate has decreased and their death rate is still quite high due to poaching. And so their population has been going down over time. So how do populations change in size? So we're back to has to being able to grow, which births and immigration, organisms moving in, play a role. And when populations shrink, you have a lot of deaths or emigration, organisms moving out. So if births and immigration are greater than deaths and emigration, your population is growing. If your births and immigration are less than your deaths and emigration, your population is shrinking. So if we look at the population of bald eagles here, we did start protecting bald eagles after they experienced problems with DDT in the 1950s and bred them in captivity to reintroduce them. So their birth rate increased over time where their death rate decreased, and that's why you see the growth in their population. All right, and so here is our honeybee populations, which we have a real problem with honeybees. So at first, our population was quite high and it was doing well, and then it started to decline because the death rate was increasing dramatically due to the use of pesticides. And here people realized we were having a serious problem and we were slowly changing what we're doing to bring that population hopefully back up. Now, what we're looking at too is this idea of exponential growth, and you've learned about an exponent before in math class. This is when your numbers increases by a certain factor, like 2 to the power of another number. So this is definitely when you're having way more births than deaths, and this curve looks like a J curve when you're having this exponential growth right here, when you're going from a small population to a large population very quickly. So this is in bacteria, which we saw reproducing down here. Bacteria are very good at growing exponentially if they have plenty of resources. Here's an elephant population. Elephants are not actually that good at doing this, but there's a graph of elephant populations. And humans, that's how we have been growing. We are growing exponentially in that J-shaped curve. So here we see human population growth again kind of level, and then we start growing exponentially right around the time that the Industrial Revolution occurred. We had a little dip there during the bubonic plague, but after that we went straight up. That's that J-shaped curve. So let's talk about me as a young child and my hamsters. So when I was a little kid, my mother went out and bought hamsters for me and my brother. They were named Petrie and Muffin. These are not the actual pictures of the hamsters. I don't have pictures from back then. This is just what I stole from the internet. So we had Petrie and Muffin. Well, it turns out that Petrie and Muffin, when we got them, were pregnant. And so hamsters usually on average have about 6 babies apiece. But we did have an accident with some of the babies initially. So we have Petrie and Muffin, and then they started having babies. So here are the babies that we had with Petrie and Muffin. Okay, so we landed up having 8 hamsters at some point. And that's because we had 6 babies, but some of the babies from the other mother died. So we had 5 females and 3 males. And so at this point, my father was nice enough to build me an enclosure with a board in between to separate out the males and the females. Well, being the little kid I was, baby hamsters are super cute. So I decided it'd be a great idea to put the 3 males in with the 5 females, which really was really bad because they're all related. And so all 5 of my females got pregnant. Okay, and there's the original Petrie and Muffin. And then I had all 5 of the other ones. And so I had 8 hamsters, and they all got pregnant, and they all started having babies. So very quickly, my population of hamsters increased exponentially, and I landed up with 38 hamsters from the 2 original hamsters in just 2 generations of births. So that's a lot of hamsters. Now at this point, my parents were angry with me because I had bred out 38 hamsters, and my mom made me get rid of all of them except for the original Petrie and Muffin. So at some point, with all those hamsters, I would have had a problem. I would have run out of space for sure. I did not have space for 38 hamsters. On top of that, my parents had just gotten me 1 big tub of food, and so I would have definitely run out of food at some point, and there was no way I could have kept 38 hamsters. All right, there was a limit to the number you can keep. So this is where logistic growth comes in. Logistic growth starts with a minimum number and then becomes limited once it reaches a certain size. So you start with very little and you go through exponential growth, and then the growth starts to slow down. And this is usually when you're running out of resources. And this is the carrying capacity for your ecosystem, the maximum number of individuals that ecosystem can hold or sustain over time. And so my curve goes from looking like a J to kind of a wonky S-shaped curve when it is logistic, because here we're running out of resources. If I had kept all 38 of my hamsters, I would have hit this wall very quickly. I would have been out of space, out of food, out of fresh water, out of fresh bedding, and then disease might run through my population at that point. So looking at these organisms, the carrying capacity is about where it levels out, because in reality, you always have a little more births, deaths, so it goes up and down like this. But the average of that is my carrying capacity. So for these guys, it's 42,000. So here's a practice question, and they made it nice and flat, which is not like reality at all. But what is the population of deer at carrying capacity? So carrying capacity is, again, where it levels off. So you look for that leveling off, and then you go across. And so you can kind of hypothesize here that it's about halfway between 60 and 80, which would be 70. During which year did the population reach its carrying capacity? Now this one's a little more realistic, where again, you start with your exponential growth, and then it's up and down, up and down, up and down. And so the average of these ups and downs is your carrying capacity, which is probably around 250. And the year that it first got there is going to be year 3, right? It's about the time it reached that 250 mark the first time. Right there. All right, the graph shows the carrying capacity for a population of grass-eating animals in the Great Plains of the United States. And now this graph is a little different. This one is not shaped like an S, but you do have your initial exponential growth, and then you have a level off here, and then it drops and there's another level off. So which explanation below is the best reason why the carrying capacity dropped? So why would your carrying capacity drop? If this is the most organisms that ecosystem can sustain, why would that decrease? Well, your ecosystem must not be able to sustain as many organisms. So what would make that happen? Right? If animals began to migrate, no, that wouldn't make that happen. They could still sustain the same number and you wouldn't see that big drop. Animals began to have more offspring between year 3 and 4. If they had more offspring, your graph would be increasing, not decreasing. C, a group of non-grass eating animals moved in this area. Well, why would that matter? They're not going to be in competition with them. Or D, the area began to experience drought. Well, if you have a drought, are you going to have as much food? No. And all of a sudden, if you have less food, then your population is going to decrease. So yes, your ecosystem could not sustain as many organisms if it didn't have as much food. All right, so let's talk limiting factors. Limiting factors basically put a check on population sizes. And so we have two categories of limiting factors. Density dependent, which depends on how closely or loosely packed organisms are, and density independent, where it doesn't really matter, it's going to kill you the same. So examples of density dependent is competition. If you have more organisms, they're going to compete over mates, over territory, things like that very closely, like penguins. Penguins compete for nesting sites, and they will peck other penguins that get within their little area, even though, and because they're closely packed, there's lots of competition. Versus tigers that are spread out, they'll fight when they come in contact, but they rarely come in contact. Disease, of course, the more closely packed you are, the more readily disease runs through, which is why in schools right now we're trying to spread kids out as much as possible. Predation, of course, so you have a predator. You think about a lion going after zebras during a migration. So they're going to be drawn to that migration because the zebras are closely packed, and they're more likely to be successful than if the zebras were all spread out. Same with parasites. Now, density independent kills you the same. These tend to be natural disasters like hurricanes, typhoons, tornadoes. It doesn't matter how you're packed, it's just going to kill you the same no matter what. So other things that play a role in our ecosystem are abiotic and biotic factors, and I think we've already talked about these before, but just to remind you, because you had to do them in your digital notebook, abiotic factors are non-living and never live. An example is weather, climate, water, soil, sunlight. And biotic factors are factors that are living or previously living, which are your food, predator-prey relationships, interactions with other species. Humans also affect population size, of course, because we destroy habitat through deforestation. We introduce diseases, unfortunately, and we also introduce non-native species like the snakehead. And I put this little link down here that you could travel to see a little video about invasive snakeheads. That's all I got for now, guys. Bye.